I see you all here in person and also people online. I will start right away with our overview, and then we'll go through the session talks. And we do have some discussion before the break today and also before the end of the session. So just to keep that in mind for questions. So my name is Simone Tilmes. I'm the co-chair of the Chemistry Climate Working Group. We also have Rafa here visiting as the outside co-chair. We have Rebecca Buchholz as our liaison, as well as Sean Homikel, who is online, and Francis Fitt is our software engineer. And so I want to give an overview of the recent work we have done in our working group, as well as especially with some focus on CSM development, CSM3 developments. And so starting with reminding you of different chemical mechanisms. So what you see on the left is the number of components, so tracers in the chemical mechanism, and those scale directly with the costs. So we do have in the past our TSMLT chemical mechanism, the troposphere, stratosphere, mesosphere, lower thermosphere chemistry. That was the most complete one for the WACAM model. And then we had our TS1 mechanism, that's the troposphere, stratosphere mechanism 1. But now for CSM3, we change our naming convention a little bit, and you will also see that in the new COM sets that will come up. We'll have a number for the tropospheric mechanisms, because those are mostly changing, while the stratospheric mechanism and middle atmosphere mechanism hasn't been changed. So we call, say, the TSMLT mechanism with the T1 MA, so T1 middle atmosphere mechanism in the new versions, and then we have T1, T2, T3, T4, T5. I'll go a little bit more into the details. For the especially production experiments that may be planned for CMIP7, and also for climate simulations, longer simulation, we now have the T4S mechanism, which is a bit of a cheaper mechanism in the troposphere, less hydrocarbon reactions and species, which actually reduces the performance by about 30, so the computer cost by about 30%, which is helpful. Then we have a specified oxidants and greenhouse gas mechanisms, really simplified troposphere chemistry to serve for production of aerosols in the troposphere and prescribed chemistry in the stratosphere. And so just another overview in terms of the model. To remind people, we have the WACAM model that is still the 140-kilometer model. We call it also the high-top model. And now the workforce for future simulation and what we're discussing on all these meetings here is really the mid-top model, 93-level model. And then there's also a low-top model version for other applications. And depending really on your science questions, you can have very different chemistry with it. Like for WACAM, you can have that full chemistry, but also just the middle atmosphere chemistry with simplified troposphere chemistry, or fully prescribed chemistry for dynamic studies. And for the tropospheric mechanism, you see here a few that I already described. Just some details also on our air quality. Sorry, I wanted to point. Our air quality chemistry, so really the more comprehensive mechanisms are the T1, T2, and T3 mechanism. But then also what you will hear about a bit today is the T5 as the halogen chemistry. Short-lived halogens are included as that will also serve better for chemistry. And we do have different aerosol schemes. We have Karma integrated in CSM development version now, and Mosaic may be integrated in the future. So if you have any questions on that. I do want to go quickly through configurations that we have now for our production experiments and planning. So as I said, we'll include the more simplified chemistry T4S. We will have an aerosol scheme that's called MEM5. So there's a fifth aerosol mode that is for the stratosphere for interactive chemistry. We do have the new dust scheme from Danny's paperwork and online emissions with our machine learning approach OASIS, and we add additional emissions to DMS as well. And then there's a lot of development still going on, and potentially we're hoping to put that in some production experiments and maybe some tier 2 experiments, like adding photolysis, interactive photolysis to UV, and Doug and June are really heavily working on this right now. Then the work you will hear about on the short-lived halogens for Rafa, Carlos, and others working on that. And then hoping to also have our updated soil NOx and others here, marinogenic emissions, methane-3 biogenic emissions. Also focusing more on improving the MEM 4 or 5 and karma chemistry, aerosol work, and we will continue including the HEMCO emissions and also including them in comsets in the future. And so what we have done so far for the development, we tested various simulations more like for present day, 1980 to 2015. And so far, the model is looking quite reasonable. We did find in the process some problems and bugs that are fixed. Like, for instance, we had some problems in our biogenic emissions in the T4S mechanism that we could fix. And so we'll continue waiting for updates from the dynamics, from the WCAM group, or from the dynamics group to continue testing our chemistry. And so one thing we also do is look at the Chem 6 physics because we want to provide also some configurations with the old physics scheme that people still can run, like finite volume grids and lower vertical resolution grids. And so Sean is also talking about it in his talk at the end of this session. That's developments in progress. Well, a lot of work in recent months also went in getting the new CMIP7 forcings that we have to use for potential CMIP7 simulations, of course. And so I will go through those in a little bit. You know, all those forcing need to be tested. And last time with CESM 2, when we included the new emissions, the model suddenly showed a very different climate. To know what is coming, what we're doing is we run a WCAM 2-degree model version that is our old, basically, configuration, but then with the CMIP6 emissions and then with the CMIP7 emissions to see what is going to happen. And Doug is leading that simulation, which is in progress. So for the forcings, we do have the volcanic forcing as a 2 emission database now available. So all the volcanoes in the past, from even from 1750, are listed here, and differences between the old data set and the new data set are basically indicated by the red points. That was the old data set that is different from the new one. So the new data set is an update done by Thomas Aubrey and others. We have a bit more different injection heights based on new observations in part, including inclusion of missing eruptions from previous data sets, satellite era improvements, especially in the last, from 1970 on, and then new smaller volcanoes, in the time before the satellite era, so we have more a balanced forcing throughout the year. And another thing we need to develop is a pre-industrial volcanic forcing SC2 emission data set to run pre-industrial with some elevated emissions. That's something what CMIT has done in the past. And those elevated emissions usually will also be used for future model runs. So we developed that with Ilaria Kraya especially. And so our new data set here tested in an we have tested it in an 1850 model run, but comparing to present day observation just to see what about the forcing would be. So this is the new forcing is in from CMIP7 is in blue, and the old is in orange. So there will not be much difference. We also ran the new data set in our T4S mid-top model, and basically the old CMIP6 data set is shown in pink, and the new CMIP7 in yellow gold, so there isn't that much difference over the Mount Pinatubo period, and as well as for later times, 1995 to 2015, for small volcanoes, it's fairly similar to what we had before. Then also Luisa, Rebecca, and Ben worked a lot on anthropogenic biomass burning forcings, and so here are two examples. What will be different? Very interestingly, carbon monoxide, for example, will be different, especially important for air quality and ozone. The old CMIP6 data were a bit higher than what we're going to see now in the new data sets. Differences are also shown in aerosols, like here primary organic matter. We do see some changes in the emissions, which will be very interesting to see what the impact will be on ozone and forcings. And then Jun also worked on the lower boundary conditions. CMIP is providing 43 greenhouse gas concentrations for CMIP7, and most of them are very similar, but one that really standed out that we're showing here is the carbonyl sulfides, because in the past we have seen, compared to observations, that we have quite a bit of an overestimation of those lower boundary conditions, so we're going to fix that as well. What we also were working on was our diagnostics. There is the ADF diagnostics, and Rebecca and Sean and others has worked hard in the last month and year to really put in some chemistry diagnostics. We now have running operationally, so you can download, GitHub this ADF diagnostic, and you do get these diagnostics already included, like ozone climatology, chemistry aerosol comparisons, budgets, AOD comparisons, CEOMOPID work, and we're still also working on WCAM diagnostics that look really nicely at the dynamics. And another data set, another comparison tool that has been developed, especially in the last year, is the Melodies-Monet framework that is very nice to do evaluation, especially of aircraft campaigns or observations like ozone zones shown here, and that really matches nicely results of specific observations, timing, and location. And Luisa will talk about that more in her talk. And then one thing, oh, now my daughter is calling. Sorry for that. So the other thing I wanted to point out is that we are actually participating in a lot of assessments and intercomparisons. And, you know, chemistry and this working group, including WCAM and ChemChem, is very active in those activities. I want to show a little bit what we have done, what we are doing right now, and what we're going to do. And we also want to learn from all of you what you're interested in to do and participate in. So we have done, of course, the CMIP6 simulations. And one thing I forgot here actually is the N2O assessment that some of us worked on in last year's work. And then we're participating in CCMI simulations. There's the big Hunga-Tonga assessment, and currently they have a working meeting at the Mesa Lab, so we don't have many contribution from people here today. We do GeoMIP work, ISOMIP, which is an interactive stratospheric aerosol model intercomparison project. We do have, we want to participate in HTAP simulations. I have a couple of slides on this here. And then also Rafa and others working on VSL-MIP. If you have questions, ask them. And for future plans, so we hope for our CMIP-ready simulations to be done, obviously the DEC and other future scenarios with, as I already said, I have a mistake, the T4S chemistry. Sorry, see, it's still in there, the wrong things. But then also GeoMIP fast-track simulation, and definitely interested in AirChem-MIP simulations, especially with our more improved model version that we're hoping to have, the VSL model version, and hopefully also with interactive methane. And so for the HTAP, Luisa and Rebecca are really leading this, and I'm not going to go through this in detail right now. But you can read it. It's really for looking at remote and long-range transport, for effects on regional sources, for effects on wildfires, methane, and so on. So there are two parts. One is more the anthropogenic, I guess, experiments, and then the fires as well that Rebecca is leading. And so I wanted to show just quickly 3 slides from other science highlights because those weren't shown by Dave yesterday. But since we have almost no time, really go quickly. Just quickly a slide from Ilaria Kraya on Hunga Tonga. She's looking at the forcing of the volcano. And secondly, Bruce is here. He is working on future oceanic emissions that are updated in the model, which are important for the ozone development in the stratosphere. And finally, we're still working a lot, actually, on our impasse grid with chemistry. Ren and Mary Barth are leading those efforts, and we're looking into more details on that. But with this, I need to stop. We are at the 15 minutes, so thank you for your attention. And I think we will, if you have any quick questions, urgent, let me know while we transition into our online presenter. And else, we will have a discussion before the break. And so then we can go into those questions in more detail. Okay. So I think we have our next presenter online. Do you want to introduce? Or I don't have it.
Yep,
yeah?
I've got it right here.
Great.
So our next presenter is Samantha Lee, who's joining us from Australia, where it is very late. So thank you for staying up to talk with us. Sam is going to talk about evaluating some initial evaluations of model and observations for a field campaign in Australia. Take it away, Sam.
Good morning, everyone, and thank you so much for having me today. I'd like to share with you some of those initial observations on some work I'm doing relative to Australian extreme bushfire events and comparing those to some models. But just to jump back a little bit and give everyone some context, in 2019 to 2020 summer season, the southeast of Australia faced one of the worst bushfire seasons in its recorded history. And in this graph here that I have, the estimates for the forest area burnt in that summer period was more than double any previous year. And this image from the NASA Worldview that I have, it was taken on December 31st of 2019. And it shows just the extent of the fires that were happening in this period in this region. Coincidentally, the characterizing organics and aerosol loading over Australia, or I will be referring to as the Koala 2020 campaign from now on, was placed in this region that I've indicated here, and it was measuring atmospheric chemistry emissions over this period. It's currently the most comprehensive smoke data set that we have for this particular region. This represents a huge opportunity for us to use this data and compare it to model outputs and see how well these models do at producing the emissions and the concentrations of the atmosphere during this very extreme smoke event. This would obviously help with future climate research and emission studies, as well as assist in air quality management and the dissemination of public health advice from stakeholders of this project. So overall, what I want to do is I want to take the koala data that we had measured in situ, and I want to compare that to ultimately 3 atmospheric climate chemistry models. And I want to see how well they represent the chemical species in the concentrations of smoke plumes during this one extreme event. And I will hopefully be able to present a range of these and their specific effectiveness within the Australian context. So this is one of the best images I was able to get from the actual koala site. And on the back of this large truck, there was this airbox, which was deployed and had multiple instruments present in it. And each of these instruments was running at some point during the December 2019 to March 2020 period. There's a large mast on top of the box, and that's about 20 meters high. So this koala data set is really a point-based data set, and it's only the surface layer of the atmosphere. So this research is only taking into account just that one layer. Just to quickly show you the diversity of the instruments that we had available at the koala site. This is just some of the chemical species that were measured over this time period. So we have a lot of data here that we are able to compare with models. But in order to do comparison, we need there to be data that is present, not only measured in koala, but also modeled in the atmospheric chemistry models. So from that, I pulled out the specific ones that are relevant to stakeholders within Australia, as well as that ones that are particularly relevant either because they have a human health impact, as well as contributing to atmospheric reactions, or are just straight up greenhouse gases. And I will give a little bit more context on ozone and PM 2.5 as I go through this presentation. I plan on comparing 3 models in this work to the point-based data, but at this time I have information for 2 of those models. And the one that I do not have information on at the moment is the WRF CMAC model, which I'm currently in the process of running with the New South Wales DQ, one of our government departments. But I'll give you some context on the AQFX. This is a regional atmospheric model, and it was developed by the CSIRO in Australia, one of our national science agencies. And thanks to Julie Noonan over at CSIRO, I was able to obtain model data from this model over the course of the 2019 to 2020 summer bushfire season here. The model was able to give a 9 kilometre by 9 kilometre resolution with averaged hourly concentrations. It's only been developed to model Australia, specifically the southeast coast of Australia. So it's a highly regional model, and it was actually developed to model smoke plumes, particularly for planned burns in the region, so that the government could then get an idea of where the plumes would head and what sort of warnings they would need to give to people nearby. I've also put here the inventories used, which they use the State Environmental Protection Agency inventories, and they've developed specific data for the fuel layer map from the AFDRS, and they've also determined experimentally their own emission factors and have used this in this particular model. The weather modeling for this was also obtained from the Bureau of Meteorology Access. I've included here an infographic from this paper, and this is the overall structure of the AQFX model. And feel free to have a look at this maybe a little bit later, ask me some questions about it, but this is the overall architecture of the model for measuring those smoke emissions. The other model that I had access to, thanks to Rebecca Bucos at your own organisation there, is the Musica model. So this is a model that was able to be obtained for 100 by 100 kilometre resolutions. And it is a global model, and people here probably have more knowledge of this model, so I won't linger here for too long. But this is another one that I'll be using for the comparisons. So to go on, I've prepared some results here just to give a preliminary understanding of what the data is looking like, and starting with ozone for those comparisons. Here we can see that the spread of ozone across that summer period was quite similar between the koala measurements and the 2 models. There was a slightly larger spread for the Musica model in this instance. I've plotted the concentration of ozone across the time series here, with the point measurements being in orange and the 2 models being present in the blue and the green. And here it was interesting to me that we could see that while there was a difference in the concentration readouts, there was really good covariance between the models and the measurements. And so this had us go to our stakeholders, and we had an interesting conversation about sometimes they don't really mind so much as to what the actual concentration is, but they want to know whether a regulatory limit has been exceeded. So I'll be speaking specifically about the Australian regulatory limits, but they start to issue health warnings when the ozone concentration exceeds 115 micrograms per metre squared. So we can turn this question into one of a categorical question. Instead of asking what the concentration was, we can ask the question of, was an exceedance event predicted? And then we get to make one of my favoritely named things in science I've come across so far, the confusion matrix. So we determine when the model got it correct in that there was an exceedance effect, when it was incorrect as to when there was not a exceedance event, and take that and make a confusion matrix. And here I've just represented AQ effects on screen left and Musica on screen right. With the green squares indicating that this is when the model was made a correct prediction, and the red is when the model made an incorrect prediction. So here it's worth noting that this is a highly unbalanced data set as well. There were more true negatives than any other category. So this will skew some of the metrics that we'll talk about just a second. There are a lot of different metrics that we can look at for this particular kind of exceedance event evaluation of a model. These are just a few of the ones I've looked at so far, which is the accuracy, how often a model is correct, how often a positive prediction is correct, which is the precision, the recall, which is how many of the positive events that it was managing to capture, and the F1 score, which is an average of the precision and the recall. When we do all that math and we plot it up on this table, it looks like the accuracy is quite high. Both of the models get to about 90%, but this is, as I mentioned earlier, because of the highly unbalanced data set. Both of the models perform quite similarly in the case of ozone, the F1 score for both of them being 0.64 and 0.6, which is not ultimately too different between the two for ozone. And I'll just quickly run through the results for the PM 2.5 as well. I've done the exact same analysis with PM 2.5 and presented those results here. With the box plots, the AQ effects model in this instance had a much lower spread of data, and it was often under-reporting the PM 2.5. And Musica came much closer to representing the actual concentrations of PM 2.5 in the atmosphere. Plotting them all again like this, and again using the New South Wales regulatory exceedance level of 16.75, we can do the same thing again. We can make the confusion matrix, determine when the model was correct and incorrect. And in this instance, the PM 2.5 data is a little bit more spread in between. And here we can see that there is actually no false positives events in the AQFX model. And that was mostly because the AQFX model underrepresented the PM 2.5 concentrations. So it rarely had a false positive, but it was more because all of the values were a bit lower than they should have been. Plotting all that up, in this case, the F1 score is quite different between the two. The AQFX had F1 score of 0.42, while Musica retained 0.73. And so in this instance, the ozone might have been better represented in the AQFX. However, Musica seems to have better represented the PM 2.5. So this is some interesting data. Both of the models covaried well with the actual environment, with AQFX representing ozone slightly better and Musica representing the PM 2.5 concentrations in this extreme bushfire event. I also just wanted to end with saying I do plan on doing an in-person visit to NSF NCAR on the 4th to the 15th of August of this year. So if you find this interesting and you'd like to talk to me about it in person and you happen to be around, I'd be more than happy to talk to you. Or if you have any other data that might be of interest to this study, happy to chat about that. Thank you very much for your time.
Thanks, Sam. We have time for one quick question, if there are any.
Thanks for the talk. I have a quick question. So where was the location of the sampling in the model, and where was the track located? It was a urban state. I mean, it was located close to the urban, into the forest, or did you evaluate the model outside of that pixels to see if the ozone evolution was different in other locations?
the Koala 2020 campaign was originally planned to measure the biogenic emissions. So it was placed about 60 kilometres south of Sydney, about 30 kilometres inland from the ocean, in just a pristine eucalypt forest. And the modelling for the AQ effects, we did a 9 kilometre by 9 kilometre grid, and I specifically looked at the grid square that was over the location of the koala campaign. And similarly, the Musica was centered across in that location, which I had in this slide right at the beginning. Yeah, here. So this is the location of the koala measurements, and both of the grid squares that I'm looking at were specifically laid over this. And it was chosen because it was relatively far away from anthropogenic sources of emissions and set in a eucalypt forest.
Next speaker, thank you again, Sam. And we're continuing the conversation about wildfire, looking at aerosols now and their relationship to temperature, and Sean Lester will be coming up to talk.
Oh, wow. Okay. Oh, thank you. Appreciate that. Sean Leister, and oh yes. Hello, everyone. My name is Sean Leister, and here I'm here to talk about some new experiments that we've created and looked at to understand simulated fire aerosol climate interactions. And how these ultimately drive hemispherically asymmetric climate responses and reduce global climate variability. So here, I just want to start with an example, starting on the small scale and moving on to the larger scale. On the left, I'm showing a global satellite image from the NOAA Discover satellite on May 31st, just a couple weeks ago. And circled in red, I'm showing Canadian wildfire smoke over large regions of North America and over the Atlantic Ocean. A few days after this image was taken, news articles were published highlighting how this smoke has been advected from Canada across these regions, nearly globally. And so we can look at the forecast of this Canadian wildfire event. And over the 10 days, we can see how first the smoke is advected eastward and then is distributed by the circulation north to south across North America. And then it's further advected eastward towards Europe. So this diagram begs the question of, since we can see these smoke from space, and we know that it's globally distributed, how does the smoke affect climate? And this question has largely gone unanswered, but a few studies have actually worked to try to understand this and answer this question. So by isolating variability in climate models, specifically here CESM2, this study found that variability in fire emissions has causes simulated sea ice to decrease faster than without. Consistent with this, another study found that variability in fire emissions drives warming across the northern hemisphere extratropics. But even though we've gained understanding from these studies, the climate impacts due to fire emissions remains uncertain, mainly because emissions are prescribed in global climate models, including CESM2. So here I'm showing the prescribed fire emissions from 1950 to 2070 across 40 to 70 degrees north, and it's shown in black. Notably, from 1997 to 2014, the fire emissions are prescribed using observations rather than historical climatology that is smoothly varying. So we see this sharp discontinuity in variability from before 1997 to after, and then from before 2014 to after, from here to here. So the results that I've just showed you on the previous slide are based on this discontinuous variability and are only over this present day period, because that's when we can understand the difference. Furthermore, and probably more important, is that the fire emissions that are prescribed in these global climate models do not match the climate state that they occur in, meaning that the prescribed emissions are prescribed regardless of the surface temperature anomaly. So it could be anomalously warm over a certain region, or anomalously cold, or it could be anomalously wet or anomalously dry. The prescribed emissions are the same year to year. And just to illustrate this point, here I'm showing the cumulative area burned in Canada with observations from 2012 to 2023, or seasonally. And we can see that the annual variations in total area burned are large, ranging anywhere from 1 million hectares to up to 16 million hectares. So the prescribed emissions do not capture this. In addition, the prescribed emissions do not capture the seasonal variability from year to year. So we cannot answer some really fundamental questions of climate-fire interactions with present-day capability in climate models, such as like how would a realistic evolution of fire emissions affect the climate? What is the long-term climate response to fires? Do fire climate feedback significantly change over time? And how important are fire emissions to regional and global climate change? So here we use the Community Earth System Model 2, or CESM2, with new interactive fire experiments to resolve this issue. And this new interactive fire experiment has 5 members, and it is taking direct prognostic calculations from CLM5, which is the land model or land component, and putting them through the coupler to the atmosphere model, or CAM6. And in order to isolate this fire response due to interactive emissions, we also compare the new interactive experiment with the prescribed experiment, the CSM2 large ensemble. And CSM2 is a very good model to use because the large ensemble has 50 members, which gives us insights into variability, and it also simulates cloud aerosol interactions, which is important to understand the fire response. And so with this, we can understand, or we can try to answer our main research questions, and which are fundamental to understanding the climate system as a whole, which are what are the impacts of interactive fire on the mean state, variability, and trends under climate change. So first, starting with the mean state. Here, I analyze the mean state by looking at mean climate responses over the individual experiment pre-industrial controls to understand the change without additional forcing. And to begin, I'm looking at primary organic matter, or POM, or primary organic matter, or POM, and specifically its burden or its mass in the atmosphere. And I'm first in the top panel, I'm showing the POM burden in the interactive experiment. And in the bottom panel, I'm showing the POM burden in the interactive minus the prescribed to understand the change due to prescribed, the change in the spatial distribution. And we can see that in the top panel, generally we see that POM burden is distributed globally, and it's concentrated over land masses, which is expected. But somewhat unexpectedly, we see that the change in pollen burden, or the spatial distribution change in pollen burden, is hemispherically asymmetric, with more pollen burden being in the interactive experiment in the southern hemisphere, up to 10 to the negative 7 to 10 to the negative 5 more pollen burden in the southern hemisphere, and less pollen burden in the northern hemisphere, from around 10 to the negative 6 to 10 to the negative 5 kilograms per meter squared. And we see that these interactive emissions drive hemispherically asymmetric mean climate responses due to these aerosol radiative effects downstream from the pollen burden differences. First, we look at the shortwave cloud radiative effect, or SWCRE, and we see that the difference, there's generally lower shortwave cloud radiative effect in the southern hemisphere and generally higher in the northern hemisphere, suggesting that clouds may be becoming more reflective over the southern hemisphere and less reflective in the northern hemisphere in the mean state. Spatially coinciding with these differences are temperature differences, since they directly depend on radiation. And we see, again, that across the southern hemisphere and the Atlantic Ocean, lower surface temperature with interactive emissions regionally by up to 1 degree less than prescribed. And near the Arctic and northern land masses, we see a rise in surface temperatures. And consistent with these results as well is a change in the distribution of precipitation, specifically a northern shift in the ITCZ. Next, we look at the variability differences caused by interactive emissions. And so again, we look at the pollen burden variability, and we look at this over the period of 1850 to 1990, since this is a period without rapid change. And we can utilize the power of ensembles to look at it. First, we see that, as expected, pollen burden variability, interannual variability, increases nearly everywhere with interactive emissions, just because they are interactive. But surprisingly, those interactive, that drives a decrease in interannual variability of many different climate fields, including the shortwave cloud radiative effects, temperature, and precipitation. And these are near global lowering of climate variability in all of these fields. Lastly, we examine the interactive emissions impact on climate trends and feedbacks. And so here I'm showing a time series of annual global mean pollen burden in each experiment respective of its pre-industrial control. And I'm showing that and I also just want to note that the similarities in the global mean are somewhat due to prescribed land use and land cover in CSM2. But notably, there are differences in the historical period and late 21st century. So that's why I'm highlighting these. And I want to understand the evolution between these two periods, over these two periods. So to understand the evolution, I plotted I'm looking at the change between the pre-industrial to 1990 versus the change from 2021 to 2100 in these different climate fields. And we can see clearly that over the historical period, there's not much change in the radiation or the shortwave cloud radiative effect or temperature. But we do see a significant northward shift of the ITZZ. But the largest evolution or growth in these fields is from 2021 to 2100, where there are large radiative effects, especially over the equator. And in surface temperature, there are a lowering of surface temperatures across the globe, especially in the northern hemisphere extratropical regions in Northeast or North America, by about more than 2 degrees Kelvin, due to interactive emissions as fires spread across the globe. Okay, so in conclusion, this study shows, I want to highlight that this study shows that these interactive emissions induce substantial hemispherically asymmetric climate responses driven by these fire aerosol climate interactions. Also, the interactive fire emissions cause persistent global decreases or reductions in interannual climate variability near globally, especially for surface temperature. And finally, the fire aerosol climate interactions reduce the trend in global mean surface temperature by about 0.8 degrees regionally throughout the 21st century, or globally throughout the 21st century. And regional reductions in surface trends can decrease by more than 2 degrees with interactive emissions.
Very much, very nice talk. I think what is really interesting is the north-south difference that comes up. And you know, interactive fire emissions seem to be something we want to have desirable in the model since it is much more interactive with the system. However, the observed fire, the prescribed emissions are somewhat observed, right? So you wonder, can we actually rely on the interactive fire emissions to give us the right signal like this difference? So what do you think, what is causing this difference? Is it because maybe our land, our rainfall, all those things may be not quite aligned with observations, or is it that the observations may lack information that we should trust more our interactive fire emissions?
Yeah, I think that the interactive fire is quite important, and because specifically that we can't rely on the prescribed fire because of these discontinuities in variability and mean responses. But the interesting thing is there are model biases in the area burned, which can cause these across the southern hemisphere and the northern hemisphere, which can cause these differences hemispherically. But yes, I do think that the differences are mainly due to the climate responses, being that the climate states do not match in the interactive from what I've seen so far, or in the prescribed from what I've seen so far. Thank you. Okay, thank you.
Thank you. We also have time at the end where we can continue as well. Our next speaker is Louisa Emmons, who will be talking about Asia AQ and analysing those observations.
Right, thank you. Yeah, okay, I think right. I just want to, so a lot of people are involved with the Asia AQ experiment and analyzing it, and we have 2 visitors this summer. I just wanted to mention Rim Kim from University of Iowa and Yifan Chang from University of Illinois are helping out with various aspects of model evaluation and analyzing the observations. So we haven't yet had sort of an overview of Musica, just in case anybody's not familiar. Our nomenclature, we're really just calling a configuration of CAM-CAM with regional refinement, Musica, version 0 and version 1 now. So we've had version 0 for quite some time with the spectral element dynamical core that you can make a refined grid in. And Musica V1 we are currently evaluating, which uses the MPAS dynamical core and has the hexagonal grid. If anyone is would like to start using Musica and is not yet, we have a lot of materials online. We have a wiki page. We've held a number of tutorials, and all that material is available from the wiki page. There are currently several grids that are available within CESM, the Arctic grid and a CONUS grid, as well as the Greenland ice sheet, a subset of this. And you can make your own grid, such as this Nori Mariscal, who just received her PhD at Wayne State, made a grid of 7 kilometers over Michigan and 100 degrees for the rest of the globe, so you can look at a very small region with refined grid, and you can even make multiple grids within one. As I said, Musica V1 is being tested. So AsiaAQ took place a little over a year ago in February and March, and was a rather complex campaign led by NASA with two NASA aircraft, a lot of ground measurements, a lot of modelers. Started out the first half of February in Manila, then went to Seoul from mid-February to mid-March, and then looked at Thailand the second half of March. And so it was really focused on looking at urban regions, so Manila. You can see that these regions are all quite different. Manila, down in the tropics, is quite isolated and relatively clean around it. This is a picture of NO2 from GEMS. Seoul has a huge megacity, and it greatly influenced by China. The Thailand region, we sampled Bangkok, but we also flew up to the north and sampled the fires in northern Thailand and Myanmar that influenced air quality. So there were a large number of measurements. The 2 aircraft worked in tandem. The white line shows the DC-8 flights, which sampled between the surface and 4 kilometers, did a lot of profiling with a huge suite of in-situ measurements, a lot of detailed chemistry, aerosols, size distributions and composition. And then a high-flying aircraft sampled out the urban region with a with a remote sensor similar to the GEMS instrument to measure NO2 columns and formaldehyde columns, as well as having a LiDAR, the HSRL, which measured ozone and aerosol profiles over these urban regions. So it's a very nice complement of detailed chemistry and detailed sampling over the urban regions. So for my work, I've been looking at Musica for this period, and I created a grid with fine resolution over each of the continents in the Northern Hemisphere, and I have a couple different versions of the grid just over Asia. So to be a bit cheaper, there's a grid with 14 kilometers over only Asia, also a 25-kilometer grid for even cheaper simulations. And we also grouped it at NCAR ran WRF with tracers, and are now using WRF Chem for the analysis. And so we're using all of these different observations to try to evaluate them. But we're currently focused on developing an emissions inventory that can be used by all the different modeling groups that were part of this campaign. There are a number of NASA-funded groups, as well as the groups in each country. And this is just an example of the different inventories that are available around Bangkok. There's a local inventory, which we think is probably most accurate. And some of the other inventories that we've used, the mix inventory is a combination of a composite of different inventories in Asia. CEDS, which is the basis for the CMIP information, emission inventory, and EDGAR. So they're all very different for Bangkok, and similarly, several different emission inventories are very different for different regions. So group in Korea is putting together a composite of all these different inventories. The fire emissions, of course, are also very different. We have FIN on the left here and QFED in the middle for one day, and so we're still evaluating whether their which is most accurate, and also looking at the VOC speciation, which we have all the detailed VOC data from the aircraft to help evaluate that. And VOCs and the anthropogenic inventories are also very different. Asia AQV3 is the first composite we used for the campaign. Propane is very different, toluene is different. So having the different ratios of these reactive hydrocarbons can make a big difference in ozone production. So now to what some other people are doing. Jun Zhang is putting together simulations using the tagging of NOx to look at the source attribution for ozone. And so we tag NO through to NO2 and all the NOI species, and then the amount of ozone that comes from a different NOx source. So this is just some of our preliminary results showing the tagged ozone. This is the total ozone, simulated ozone, and then versus anthropogenic or fire from ozone for these two sites in the Philippines, Manila, and a more remote site. So clearly up north where there was some fire influence, they're comparable, but in the city, they're anthropogenic is more important. And Hayram is doing some similar work, source attribution, a completely different method in WRF Chem, and that is, or WRF CMAC. So we'll compare with that. And Yifan Cheng, visiting from Illinois, is working on updating the representation of urban properties in the land model and looking at how that impacts ozone air quality. And so she's just started, but she's already made great progress, and I'd have results if the computers hadn't been down for the past week. But so we can, this is really valuable for Asia AQ, which was really focused on understanding the air quality in these urban regions. So there's a USERF data set that was that she's implementing, and it changes the properties, the thermal, morphological, and radiative properties for things like the roofs, canyon floors, and walls of the buildings within the urban regions. So she has done a little bit of a run already with, she's using the grid I made with the 3 fine resolution regions over North America, Europe, and Asia. And you can't really see that, but so this is the control and the surface level. So in general, the ozone amounts are the same, but if you look at a difference plot, you can see in urban regions, we see quite some large differences, some plus or minus at least half a BPB in some of these urban regions. And next, Wenfu is testing out Musica V1. She has just started getting some good results. And so this is, she set up the MPAS grid. Beiruz and others have been helping as well. Set up a 3-kilometer grid that covers the Philippines and Taiwan for our regions, with 60 kilometers for the rest of the globe. And so this will also be a really great test of this high resolution, and I think will really help us understand these observations. So sorry, for a lot of this work, we'd really like to use melodies, which we've been developing over the past few years. And any day now, version 1 will be released, and it allows for, as Simone mentioned before, allows for detailed comparisons of observations to models, so matching the exact time and location. The atmospheric diagnostic framework that we've been also using is more for climatological comparison for long model runs and with climatologies of observations, but for analyzing specific aircraft campaigns and using surface observations like the EPA Air Now data, Melodies Monet is set up to do this exact comparison. And so we have a number of data sets all set to read in it, aircraft campaigns that are in ICART format, a variety of different satellite products, and Some development versions have Pandora, and we're also working on reading in the GEMS data. So the framework has readers for each of these different observations, puts them into a standard format, can read a variety of models. I didn't list that, but CESM FP, CSM with the spectral element, WorfChem, variety of other models. And then you set up what you want, what sort of comparisons you want to do in a YAML file, and you don't have to write any code. And then the driver pairs the model with the observations, and then you end up with paired data, and plots and statistics are generated. So it makes plots like these. The model overlaid with the air now observations, and then box plots, violin plots, whatever you want. For Asia AQ, this is just an example of WorfChem and some Asia AQ observations. So you can have time series, you can have a curtain plot of the model as well as the observations as a function of altitude and time, and vertical profiles comparing the observations and models as a function of altitude for each species over whatever region you want. And it's just an example. We also can compare with Moppet and see, get difference plots over the whole map. So there's going to be a large Asia AQ model intercomparison once we decide on get a finalized model emissions inventory, and so we'll be participating in that. And I just want to say that we welcome users for Melodies, Monet, and Musica, and welcome your contributions and testing of them. Thanks.
It says for Louisa. What's that?
Go ahead.
From Musica, what is the driving reason for us to switch the dynamical cores?
Will allow us to go down to the finer resolution of 3 kilometers. So the Musica V1 spectral element, we really can't run below about 7 kilometers. Did I say that right? So with the MPAS core, we'll be able to go down to 1 kilometer. We currently have grids that are centered at 3 kilometers.
Okay, let's move on to our next speaker before the discussion. Saida Mohammadi will be talking about volatile methyl siloxane and the oxidation, aerosol formation, and aging.
Sorry. The first slide. I wanted to see how to use pointer. Okay.
Yeah, so
This one?
Yes.
Okay.
And just point right at it.
All right. Thank you. Hello, everyone. I'm Saide, PhD student from University of Iowa, and I'm going to present our work of modeling volatile methyl siloxane, or VMS, oxidation, SOA formation, and aging using CSM2 and Musica version 0 framework. Outline of presentation, I'm going to start with a little background of VMS compound and the motivation, moving to model setup, simulations, and then I will dive into the result and model evaluation, and then end it with key takeaways and representing feature works. What we know about volatile methyl siloxane is that they are synthetic compound, high volume, human-made, and they're characterized with silicon oxygen, the alternating silicon oxygen bond with 2 methyl group attached to silicon. They are found in mostly in personal care product and also industrial lubricant, glues, and cleaning detergent. Some of the important cyclic volatile methyl siloxanes are D4, D5, D6, with the number representing the number of silicon in their structure. And D5 is one of the predominant and ubiquitous CVMS in the atmosphere. So about the fate of VMS in the atmosphere is that whenever you apply your personal care product, they are highly volatile. More than 90% can evaporate, go to the atmosphere, and finally they can react with hydroxyl radicals and with a few to several days of lifetime in the atmosphere. Comparing the global D5 to other anthropogenic emissions like benzene is not too much, but this is not the whole story about the D5 in the atmosphere. They have a potential of long-range transport. They also are classified as very persistent, very bioaccumulative under Stockholm Convention on persistent organic pollutants list at 2023. And all the evidence of aerosol formation of this compound are listed here. All these studies are either chamber experiment or oxidation flow reactor, so experimental work, or few of them are field campaign. The most recent one, which is published from our collaborator when we did field campaign in New York City during 2022 summertime, is Mipich et al. It was a combination of lab work and also field campaign. When we observe, and this figure represents that the oxidation product of D5 that were present in a particulate matter sample collected from New York, you can see the first generation oxidation product with 1 hydroxyl group substituted to methyl group, and also the second generation in New York City samples. So the one important key takeaways from all these studies and also the New York City field campaign in our work is that the oxidation chemistry of D5 is actually multi-generational. Why do we need to model CVMS? Because of the widespread use and the emission, and also the potential of long-range transport, and the bioaccumulation and being persistent in the atmosphere. And we also have the available gas and particle concentration due to the NYC Mets field campaign during 2022. So we can evaluate the model. And also the parent and daughter compounds proposed as a tracer of personal care product. But a specific daughter molecules, their lifetime, their first partitioning are also needed. Here is what how we modified the musical model. So for the emission of VMS compound, we use the Brunei et al. 2025, which is the other collaborator of this research. We just submitted the manuscript last week. And for this, I started the simulation with CamCam because of the computational cost. We wanted to see the reasonable result for SOA with 1 degree resolution, and then we moved on to regraded in musical resolution with finer resolution. And we have 2 sets of reaction mechanism for CamCam simulation. We wanted to see actually the SOA formation of D5 at the first step, and also we wanted to study the aging effect of aerosol. We didn't consider silicon conservation in the reaction mechanism at the very first step of our simulation. And the Musica simulation is with much more updated mechanism. And also we wanted to see the multi-generational and aging with silicon conservation method. Here is a schematic of the VMS emission from Brunei et al. 2024. So what they did is that they took sales data and also sales data for personal care product and population density, and they scaled the per capita emission globally. And this figure shows the gridded emission for Musica grid with 14 kilometer over CONUS and around 100 kilometer for the rest of the world. The big caveat in this emission file is that we only use the data from personal care product usage, not industry, not water treatment plant. The reason is that there are not any available data from industry or other sections. And also, Brunei et al. Did an evaluation of actually D5 emission with this method, and it was in very good agreement with measurements. Here is the zoom of D5 emission over CONUS. You can see the pattern of the hotspot in the CONUS is mostly over the urban areas with high population density. For example, New York City with one of the hottest spots over CONUS, comparing to Chicago. And I also included Denver, Colorado emission. You can see how it correlates with population map. So the SOA formation in CAM-CHEM is based on the volatility basis set scheme. So in the VBS, actually VBS tracks the VOC oxidation product by their volatility, and by distributing the product in 5 volatility bins that they can further partition to the aerosol phase. With the first bin being least volatile, the most probability to partition to the aerosol phase, and the last bin being the highly volatile oxidation product with less potential of aerosol formation. And this reaction mechanism shows the general mechanism, which how we define aerosol formation in the model. These coefficients alpha over for the SOAGs are actually experimentally so these molar yields are defined based on the experimental work. As we see here for specifically D5, this figure is SOA yield versus OH exposure, and the second axis represents the equivalent photochemical age days. And all these data are available SOA yield for D5 from different studies. And these dashed yellow line represent the 5 days, which is about a 1 lifetime of D5. And here, the highlighted area represent the more atmospherically relevant environmental condition, experimental condition. So this is basically the same data, but the other way of showing that the SOA yield versus D5 reacted. What we did was we fit this line for all these data, and best molar yields chosen via non-negative linear least squares. Here is how we define the D5 aerosol formation. As you can see, most of the molar yields are only distributed over 2 bins. The first bin, which mostly are less volatile and are in the aerosol phase, and the last bin, which most of the oxidation product are in the gas phase. And we also use the extended version of VBS. In the extended version of VBS, each of the SOA are assigned to their source. So in the CSM default, there is SOAs from fossil fuel, presented as SOAG-FF, biomass burning BB, and biogenic BG. And what we did when we wanted to add the D5 SOA, we put all the SOAs from fossil fuel and biomass burning and assigned the SOA GFF for all of those sources. And we assigned the SOA from D5 to SOA GBB and kept the biogenics as SOA BG. Here is how we define the reaction mechanism. We represented the gas phase oxidation product of D5, the first step, and OD5 actually is the bulk oxidation product, and which can also, D5 can also form the aerosol in this reaction mechanism. For the simulation, when we wanted to see the effect of aging, for the case that we have D5SOA and aging, we represented the aging for considering functionalization only, where each of these volatility bins can move one bin lower, knowing as functionalization aging, and represented in the second case of simulations. Here is the global distribution of the 5 species. As you can see here, the hotspot and highest concentration of D5 are mostly distributed over urban areas like Europe, China, east and west of United States. But however, the oxidation products are almost everywhere distributed in northern hemisphere. As you can see also in Arctic, you can see some concentration showing the long-range transport. This figure shows actually the SOA from D5. As you can see, the pattern of hotspot matches with D5 concentration, confirming that most of the SOA from D5 actually are highest wherever we have high concentration of D5. Here is the detailed volatility basis set, each bin's diurnal profile of D5 species for semi-volatile oxidation product and actually aerosol phase. I wanted to see the aging effect by including 2 cases. In all figures, orange solid line represent the D5 SOA, and the blue one is D5 SOA with considering aging. So to take a closer look, you can see in the bins that we had the 0 molar yield for the oxidation, for the SOA formation. We have the 0 concentration in this bin when we don't have aging. But when we included aging case, we can see the formation of aerosol. So in these 2 figures are a total semi-volatile and aerosol. You can see how aging can increase the aerosols from D5. And this figures actually shows the same thing, but with a special distribution for no aging case and aging case, and these 2 figures shows how aging affect the aerosol formation. And this figure actually is for the particle phase. We can see in the aging, there is increase in aerosols when we represent the functionalization, but the less gas phase, semi-volatile oxidation product. So we evaluated the D5-derived SOA for both model, aging and no aging. So with aging, we can see the higher aerosol comparing the no aging. And we evaluating with the measurement with NYC METS sampling during July 2022 in New York City, which for 4 samples, the value was 6.6 nanogram per cubic meter. So both model actually underestimate SOA, D5 SOA by factor of 3 for aging. So aging is doing a better job of capturing the D5 SOA, but we have not yet apportioned the error to emission, SOA yield, mechanism, resolution effect, or even it can be due to the analytical uncertainty that we are working on that. And we evaluated the other parameter in the model, PM2.5 and ozone. For the PM2.5, you can see the black and red line overlaid for aging and no aging cases, which shows that D5 aging shows minimal effect in other variables like ozone and PM2.5, but the ozone generally underestimate PM2.5 with good agreement with daily trend, and for the ozone, it overestimates. And overall, we saw the D5 peaks in urban area, and we saw the pattern of northern hemispheric and long-range transport. The aging effect actually enhanced the aerosol formation from D5 without any impact on any other variables. And it underestimates PM2.5, overestimates ozone. And as a future work, actually I submitted all these musical simulations, but due to the maintenance, they are still on queue. So looking forward, the next step is doing the higher resolution musical simulation with updated D5 chemistry. We wanted the result will be more consistent with experimental data, specifically with Kang et al., where they did experimental work to show the VBS from the D5. They showed that how the first generation oxidation product actually are very volatile. They don't form aerosol at the very first step of oxidation, and then they can further oxidize and form aerosol. So these are the simulations that I'm gonna do for musical cases to see multi-generational aging effect. And I acknowledge my advisor, Dr. Stanier, and collaborator from University of Iowa, University of Colorado Boulder, and Dr. Joe from Seoul National University, and scientists here at NCAR. Thank you.
Maybe time for one quick question before our discussion.
Just a quick question. So what's the lifetime of the D5 VMS? I couldn't quite figure that out.
Based on the experimental work, there is a quite wide range of D5 lifetime in each of studies, but there is a range for that. If you consider chlorine radical oxidation, the lifetime is going to be much lower, starting from 4 days or 3 days, and spanning to around 8 days. So it's something between 4 days to 8 days. Yeah. Thank you. Yeah, thanks.
Okay, that was great. Thanks for all the speakers. We do have 10 minutes now or something like that before the coffee break. We do want to pick up on some questions that people raised earlier. Maybe we can just, we could go back to the first slide set on the introduction to have some start of a discussion. So are there any general questions to the model? We do have another discussion later on to the setup of the model to CESM3 experiments. And you can think about that. One thing I think I do want to come back was a little bit the question on the dynamical course, because we had very little time to answer that, maybe, because one question that I still have, and maybe when Fu is here as well, is on the dynamic course, really we can go to 7 kilometers with the spectral element in the regional refinement. For MPAS, I think, or my understanding is that currently in the global model, the cloud resolving parameterizations aren't quite included yet. Is that correct? Because we can develop these high resolution versions, but do we actually parameterize the clouds properly? Or are we actually, do we not parameterize the clouds, or do we parameterize them still in the model for the MPAS grid?
Right person to answer this question, but so for us using musical MPAS is just a dynamic core, so the physics is still from CAM. I think that's a question we need to ask the CAM team if they have developed or updated cloud schemes for that.
actually part of the CIMA development, that we will have cloud resolving physics. I just want to, I think it doesn't have the physics changes yet.
Have to be made to, for the non-hydrostatic dynamic core or for the convection resolving.
So maybe while you're here, you can also explain a little bit how easy it is to develop a grid for the MPAS model version, because, yeah, that maybe.
There's some details you need to figure out, and if you have experience with Musica version 0, it will not be hard to use Musica version 1. Although we are just started testing if it works. It runs for now, but we haven't really looked at the results to check if the results is reasonable. If after we check the results is reasonable, we will have a tutorial soon, hopefully in July. But as I said, you might need to have some Musica version 0 experience before you can move to Musica version 1, because there are it's doable, but there's so many details to figure out. Yes.
Maybe we can hand it around, or yeah.
That's the MPAS configuration. Is based on CAMs. I mean, it uses CAM 6 or 7 or both, or for Musica version 1.
So we've tested Musica MPAS in CESM 3, so that's CAM 7, right? Yeah, you can specify either one.
For people, we have two versions. CSM3 basically is the new development version that we are developing going forward. And one thing is CAM7 will have new changes to vertical resolution and physics and other things. But there's also a CAM6 physics version available that we are testing, and those are slightly different, or actually in some major parts they will be different. And so there will be those two CAM7 and CAM6 versions available. Currently, probably the CAM6 physics version is the one we understand better, because the CAM7 version is still in development. That doesn't mean we can test it and look at it, obviously, and do that. Other question to dynamic cores or model setup? Yes? It should work.
So I'm really very ignorant here, but then from the CAM perspective, because I heard that the home dynamical core is being introduced to CAM, and then you will have the non-hydrostatic version down the road. So that's the cube sphere and so on. So from that perspective, it might make sense to stick to maybe still like pay attention to the SE die core and the cube sphere grid and so on, keeping that like a development in mind.
The core is a spectral element.
So because the CAM7 is already using spectral element, right?
Yes.
So I think they are using not, a hydrostatic version, if I'm understanding correctly. But Mark Taylor, Christiana Yanovsky, so they have the ongoing effort to introduce the non-hydrostatic version of SE. I think that's going on right now.
Good, because that will allow then probably the spectral element regional refinement to go higher resolution as well.
Right.
Okay.
I think Adam Harrington has been working a lot in that directions, and so he showed a diamond simulation, so like a convection permitting a resolution simulation. So keep that in mind. It would be useful.
And thank you. Yeah. Yeah, we need to keep track of everything. Yeah. Okay. I mean, other questions. I have brought up the different multimodal comparison projects that we have. I'm sorry, I'm going here the wrong direction, as well as the diagnostics. And I don't know what time it is now. We only have 1 minute. We can also just go to the coffee break and continue with this discussion after the break. So why don't we have a coffee break now, and then we'll talk about multimodal comparison projects and other questions at the end of the next part of the session. Okay, thank you. And all the speakers again in the morning session. And see you after the break. Because online people may be there already. So while people coming in, our first speaker is Rafael Fernandez, and he will talk about Arctic halogens reduce ozone in the northern mid-latitudes. And should we give you a notice after like 2 minutes?
Yeah, sure. Yeah, you can just let me know. Well, thank you very much, everyone. I'm Rafael Fernandez from the National Research Council of Argentina, and I'm presenting these results I made with some of my students back in Argentina and in close cooperation with Carlos Cuevas and Alfonso Saiz Lopez from the CSIC in Madrid, Spain, where I've been working many years, and also with help with Doug and Simone here at NCAR and many other folks. So, ozone depletion events are processes occurring in the Arctic which are related with heterogeneous recycling chemistry. During these ODEs, oops, right there, okay, there it goes.
You can point, yeah.
Yes. So during these ODEs, there is a strong depletion of ozone from background levels of about 30 ppbs, for example, to sometimes to detection limits, almost zero, mostly during the spring. And this are the records of ozone levels during the Mosaic campaign that was on board of a ship going to the North Pole. And during this event, it is well known that halogens play a very active role. So there is a process called or simplified as a bromine explosion. And in these processes, high levels of bromine monoxide, and also we know that iodine also plays a large role, and they dominate the ozone depletion during those processes, mostly during the spring. So what we wanted to answer was, okay, so if that's happening widespread over the Arctic, what's the impact when those air masses go into the northern mid-latitudes? So for doing that, we used the Polar Halogens module we developed a few years ago in Camp 4. This scheme or this module has 3 additional sources of halogens arising from the Arctic sea ice. One is the photochemical release of bromine and chlorine, which is mostly arising from the first-year sea ice after, photochemically driven. And then the other one, the second one, is the brine diffusion of iodine produced, biologically produced underneath the sea ice. And then the third process is once all these species are emitted to the atmosphere and the partitioning between all the halogen reservoirs and reactive species, they can be trapped by sea salt aerosols or deposit over the snowpack, and then they can photochemically recycling, and which constitute the third process, which adapts to what we normally call our halogen emissions, which considers basically only oceanic emissions of halocarbons and molecular iodine. So these processes, which are quite complex, we just parameterize them as good as we could for a global model. And this includes many fields that are that we keep track in the model and with the coupling of the ocean and with the ice. So one of the parameters, the most important one, is the changes and the seasonal changes in the first year and multi-year sea ice coverage occurring in this case over the Arctic. Also, we need to consider the net solar irradiance reaching the Arctic surface for the different time periods. and we compute that using the cosine of the solar zenith angle, and this is shown here on the right for different seasons. And then, for sure, we consider the instantaneous surface air temperature and the deposition of the halogen species at different grid points, particularly over ice. And then it's really important to keep track of the chemical partitioning between reactive and reservoir halogen species, which in turn depends on the background NOx levels and air pollution that we have. So another question we wanted to answer was if the impact of halogens from the Arctic has changed from the pre-industrial period to present day. So these are our model experiments. In next results, I will show always results. The no halogen simulation, that means the standard CAM-CHEM chemical mechanism is shown in gray. Whenever we add halogens, that's a typical configuration that we usually work with. We include the oceanic emissions, which will be shown in blue. And then when we consider both the oceanic plus the sea ice emissions, I'll show those results in red. And we will consider two different bands, the Arctic latitudinal band. This is pointing like to the side, okay. So the Arctic latitudinal band, which goes from 60 degrees north to the pole, and an equivalent, a region, with equivalent area, which is from 47 degrees north to 60 degrees north, okay, which has the same area as the polar cap. And we perform 5 years long cyclical simulations for the present day and for the pre-industrial period. Considering for each one of them the lower boundary conditions, the sea ice conditions for each of the periods, but forcing with meteorological fields from present day, okay, from a previous simulation, and using the low resolution, the 2 degrees horizontal resolution and 26 vertical levels standard in CESM1. So, and for the validation, we basically compare with two different type of data sets. One is the climatology of the ozone zone climatology from TILMS 2012, which recognizes the different behavior of Arctic ozone on the northwest, and on the northeast. Okay, and I will show that a little bit later. And also compare with some observations, surface observations from NOAA and from the EVAS database at different locations, which are shown there in the map. So moving into the results, here on the top left, in the panel A, we can see that the observations are in black with the hourly variability on each of these error bars on each of the black lines. And then the model results for the no halogen simulation are in gray, for the oceanic configuration are in blue, and for the one including the sea emissions are shown in red. So we can clearly see that observations, the minimum observed during the spring, the minimum of zone observed over the Arctic during the spring in the West Arctic is only captured when we include these sea ice emissions. We can also see that on the vertical profiles of the ozone zones, when we do the average during March, April, and May, I mean, in the free troposphere, basically, it doesn't matter if we use the oceanic or the oceanic plus ice simulation. The vertical profiles is more or less similar, but both of them show better agreement with observation compared to the no halogen configuration. But then close to the surface, perhaps the model overestimate a little bit the reactions in ozone, but then it's the only way we can capture some of the values at the surface using this scheme. If we move to the East Arctic, we can see that basically the three model configuration are overlap. The more halogens we meet, the less ozone that we have, but they more or less show the same seasonal cycle, and the model reproduce that well. So in the central panel, we can see the surface ozone percentage change and the latitudinal variation of the ozone change. And we can see that there is a pronounced latitudinal gradient, which can affect regions in the northern mid-latitudes. And that's how we zoom in this next slide. Okay, so here we show, I forgot to mention here, so this is for the pointer. So the changes in ozone that I will show are the changes between the, are the changes between the red and the blue simulation, okay? So now all the differences in ozone are between the red and the blue. And what we can see is that these Arctic halogens, the export of these low ozone and halogen-rich air masses from the Arctic can influence the background ozone level in North America and in Europe. And these lines over here show the percentage surface ozone changes within each of these regions that we have highlighted there. And it's about 5 to 6% in the northeast US and in Northern Europe, and a little bit larger if we consider the whole latitudinal band, okay, where we can have values up to 11% reductions when we include these Arctic halogens on the monthly mean. So to compare these results in the latitudinal bands I mentioned before, so in this light blue are the Arctic latitudinal band, where we can see a maximum reduction of about 16 to 17 ppts, which is about 40% of the ozone, surface ozone in this region. If we focus on the northern hemisphere mid-latitude, that reduction can reach up to 11%, which are 4 ppbs on the spring monthly mean that we get in the model. And if we go into the northern hemisphere annual mean, this only represents 2%. So this is showing and highlighting that these Arctic halogens emissions are important on a seasonal and local scale, but I mean, it won't affect the global mean, but then on a regional scale, in the springtime, it is important. And why is that? Why do we have these springtime pools? And that's because emissions increase during the spring because of the opposite behavior of changing in sea ice coverage and changing in solar radiation reaching the Arctic when moving from winter to the summer, which both of them, they have the multiplication of those fields maximized during the spring. And then also because there is a pronounced change in partitioning between reactive versus reservoir species of halogens. These are the dots here, the blue dots for bromine and the red dots for iodine. On the right axis, this is a ratio of the reactive versus the reservoir fraction, which maximize for bromine during March and for iodine during April and May. And this is why on the second panel, where we compare all the chemical loss by families, we see that most of the chemical loss is driven in the Arctic region by halogens, and mostly during the spring. And most notably, the ozone difference, I mean, the change in the difference in ozone here. So the blue line is the contribution for the oceanic emissions of halogens, and the red bars, the red part of the bars, is the contribution of the sea ice emissions of halogens and how they both contribute to the total ozone reduction in the Arctic. If we move that to the northern mid-latitudes, so what's the main difference? So ozone destruction is not due to halogens. It's mostly dominated by HOX and NOx. But then during the spring, there is still up to 40% of the total reduction is also driven by halogens. So finally, we just compare how were these impacts between the present day and the pre-industrial time. Okay, and the basic answer is during present day, there is more tropospheric ozone. So then the absolute ozone changes are larger. But then during pre-industrial time, there is less ozone, but then there is also less NOx and less HOX, and then the partitioning is shifted to reactive species. So that proportionally, the halogens have a larger impact in pre-industrial time than in present times, which is also shown here. Okay, so the black line is the change, the ozone change during present day, the gray line is during pre-industrial time, and the red line shows that the difference is larger during pre-industrial than during the present day if you compare in relative terms. So this is our results. The main conclusions are that the regional export of these halogen-rich and ozone-poor air masses affect the northern mid-latitudes, and that these seasonal behaviors is only captured when we include these halogen emissions in the model. So thank you very much, and I'm happy to take some questions.
Are there any questions? Please come to the microphone. I do have one while you line up, maybe? I don't know. It looked like you had a question. Okay, I just have a question in terms of, this is really important, and I think, does it require VSL chemistry, or do you just need somewhat emissions that we add to the model framework? So do we have to have a certain configuration to implement that in the current model version?
So yeah, actually yes, the halogen emissions from the CIs are computed online. So it's not an offline set of emissions that we can implement. Like the halogen development, we have offline emissions of halocarbons and then online emissions of oceanic iodine, and then these CIs halogens are also computed online.
So we could basically, it does require the halogen chemistry though?
Yeah.
Yeah.
Yeah, it requires the halogen chemistry to be active. Yeah.
Very nice talk. So you have a polar module, which is specialized to get the right amount of emissions in the high latitude regions. And you showed only the Arctic today. Now, do you use the same polar module for the Arctic as you do in the Antarctic? And what's the difference between reactive halogens between the two regions?
So that's a great question, Doug. So yes, we use the model. We have the polar module actually works in the Arctic and in Antarctica. CamChem overestimates quite much the absolute levels of ozone in Antarctica over Antarctica. And we haven't been able to reproduce exactly the observations that were shown for ozone. I mean, we have the polar module validated with all the reactive halogen species, both in the Arctic and in Antarctica, but because of some additional reactions missing or some transport issues missing in the model does not reproduce well ozone over the Antarctica. Okay, and the partitioning is different. It's much more different because in Antarctica, in the southern hemisphere, there is much less NOx, and then everything, all the halogen is more partitioned into the reactive phase, so it's proportionally more efficient destroying ozone in in Antarctica than in the Arctic. Okay, that would be the answer.
And we move to our next speaker, Ben Gobert. He will talk about investigating the role of chemistry on the methane budget in emission-driven methane simulations.
All right, good morning, everyone. I have lots to cover, so this was funded by NOAA, and it's a collaboration with University of Arizona. Especially Amin has been doing a lot of the work, and we're using the short-lived halogen from Rafa, Doug, and others. I'm using methane emissions from a various products, especially NOAA. So the goal is to do emission-driven simulation, is to use emission-driven simulation of methane, so we can represent the emission, the chemistry, and the climate feedback, understand the methane budget, evaluating the impact of chemistry and chemistry change on the methane growth rate, include chemical feedback, and include various processes between those emissions and chemistry. Chemistry climate models do overestimate OH, they have a larger uncertainties, and people have been using messy chloroform inversions. Instead of chemistry climate models, we tend to even disregard chemistry climate models, even though we do represent a prognostic OH, representing all of these different processes, including many chemical reactions. And so we want to reconcile those estimates. And there are also issues on the latitudinal and temporal distribution of OH, which I'm going to get into. So one of the things is the underestimation of CO. There are many, many papers, and it's not really understood why it's going on. And so this is an older one. This is the most recent one, where IR Chemic, which is one of the most recent intercomparison of chemistry climate models, here compared with CEO measurements from Greenland ice core, is showing that not only we overestimate OH, and though we underestimate CO, we have been doing this for the entire record. So here I'm using the newly implemented CESM 2.2 short-lived halogen representation that Rafa Fernandez developed. Paper is in preparation. And we've been contrasting this with the Mozart TS 1.2, the standard chemistry of CSM2. And we did contrast those simulations in prescribed using the CMIP6 methane concentration fields and 3 other simulations using 3 different emission inventories. And we contrast them all, so you get a double of chemistry and emissions and prescription in all of them. This is 5-year simulation to look at 2016-2018 results with atom observations initially. So if you look at atom OH with and without halogen, you improve OH, especially in the winter and spring of the mid-latitude and the high latitudes. And we do reduce ozone, and this is a non-result of the impact of halogen representation. It just wanted to take advantage of the OH observations during atom here. So if you look into the latitudinal distribution of land versus ocean, and at the surface versus tropospheric differences, you can see that OH is reduced mainly over the ocean and over the troposphere, and with some increase of the secondary OH sources over land, which tend to compensate, and that we reduce slightly more OH in the northern hemisphere, so we don't change the interhemispheric ratio, which is very important for as a metric of methylchloroform OH proxies. And the mechanism is a reduction of ozone, which gives you a reduction of ozone photolysis, primary source of OH, and the secondary ozone recycling of OH through HO2. And the net would be mostly a reduction of OH over the ocean and increase over land. So in terms of methane loss, in our default, we have 573 teragrams of methane per year loss for 2017. In the TS 1.2, if we're using emission-driven, we have a range of values from 561 to 573. And when we introduce the SLH, we move on to 504, which is more, those 3 different simulations have the same thing, which shows that there is less spread with methane emissions. And this one has higher methane emissions, leads to higher loss. And so it's typically around 500 for the methane plus OH, and an increase an increase by 16 teragrams for the chlorine sink, which gives you 520, and a methane tropospheric chemical lifetime increase by around a year. Now, if you do another sensitivity where you use a different set of CO emissions, you can have up to 9 teragrams of methane change, which is mainly appreciated in emission-driven simulation. So Wild et al. Did lots of sensitivity of comparison of tropospheric ozone burden versus methane lifetime, where they look at emissions, isoprene emissions, lightning NOx, and deposition, and other things. So I wanted to redo this plot, looking at in the light of the halogen chemistry. And so from here, we move on from a high ozone, although in line with the tropospheric ozone burden estimate from TOR 1, which is observationally based, and methane lifetime here. So good ozone, but underestimation of methane lifetime. And with the halogen now, we move here, where we underestimate ozone burden, but we do have a better lifetime. And then this sensitivity is the lightning NOx, which has been shown to be the most important parameter for methane lifetime in CESM in this paper. That red line here. So this is a conundrum. We should be using these in the way we define the new chemistry for future simulation. So it keeps going. So now I did 20 years simulation where I'm comparing prescribed versus emission-driven using the new carbon tracker methane released posterior emissions, where they're using, I should say, they're using isotopes to constrain both the total methane emitted and the partitioning between the microbial and fossil fuel sources. So here I'm using MOPIT. I've been decomposing the time series. And so now we do have underestimation of CO in the northern hemisphere that is not as bad as before, and an overestimation for tropics and southern hemisphere. And if you look at the interannual variability, you can see that we are actually reproducing very well the changes that are mostly due to fires if you detrend, and that the fin emissions are actually very good at representing those. Although sometimes we do have fires that are not in the record, and sometimes some fires in the Arctic 2021 is not well represented here. But if you look at the seasonal cycle, we now overestimate CO, which means that we still have work to do in the spring, and but we underestimate CO during the summer. So there's still a lot to do on photochemistry, secondary sources, representation of especially emissions from fires, biogenic and anthropogenic sources. Here is GOSAT methane observations that only started in 2010. We do now better represent methane in the emission-driven than in the prescribed simulation run, which is kind of interesting because especially over this period, the methane is supposedly prescribed by observation. So it really has to do with the spatial distribution of zonal mean methane emissions versus having actual 1 by 1 degree maps of monthly emissions. We do see that the impact of the overestimation of the underestimation of OH in the southern hemisphere has an impact where methane is starting to grow too much and actually reverse the errors. But overall, it's similar performance or better in emission-driven for the methane observations comparison. This is showing the same thing for aircraft in situ profiles for HIPPO 125, ATOM 124, so for the, but arranged by season and from different latitudes, latitudinal bands, and you can see the same thing where we tend to do better in the northern hemisphere, but then having a overestimation in the emission-driven runs for the southern hemisphere. And so this is consistent with both GOSAT and MOPIT for two different campaigns that were made mainly over the ocean. If you look over land, so these are two different campaigns that were based out of Seoul in South Korea and then go flying around, especially Eclipse was flying over the ocean, and so in the open ocean. So this is representative of actually East Asia. And we do better in the emission-driven, although we tend to overestimate the local emissions from South Korea. But this is really, it looks really good compared to observations. So we do have a higher burden in the CSM methane, as shown to be better with GOSAT. And this translates into a higher methane loss, which means that our system is, with our OH prognostic array, is actually well buffered and tend to dampen the methane perturbation so that the differences between the two runs are not as large and would give you a methane lifetime that would be similar between the two. So In summary, our updated representation of CSM2 allows us to better represent simultaneously a better ozone, OH, CO, methane, and other related oxidants, as shown by aircraft observations and satellite columns of CO and methane, as well as NDAC, that didn't show here. And that we do now overestimate CO in the spring and underestimate in the summer, and we overestimate, we do have a better OH in the northern hemisphere, but that comes at the cost of more work to be done in tropics and the southern hemisphere. And so we can now do emission-driven simulations that are better than the prescribed one, and that our methane chemical loss, especially through secondary OH sources that are modified in the halogen representation, is much better and well buffered compared to perturbation, and so we will look into OH trends next. Thank you.
Nice talk, Ben. So can you go to the vertical profiles, the comparison with the yeah, that one. So you say that the emission-driven overestimate a little bit. That's for year 2022 on the right. But then, if I don't remember wrong, your plot, your trend on total methane emission for the emission-driven simulation also overestimates moving into the latest period of the simulation. So is this local or this is global overestimation? It's very local.
Yeah, this is over the entire latitudinal band. So yeah, we do tend to underestimate towards the end of the record, for sure. Yeah.
So based on your emission results here, are you suggesting that CMIP7 should go, should emit methane instead of?
CMIP7 emission, I've not done that yet. But that would be next step, and fire emissions.
Yeah. Yeah, I think after in the discussion we can talk a little bit about what simulations we want to aim forward. Maybe that would be another point to discuss. Is there any more questions? Else we welcome our next speaker, Chuan Peng. Is that right? Yes. Okay. Again on methane, distinct efficacy of regional emissions in affecting global methane concentration. I guess I should go to the microphone. A global modeling study with interactive methane chemistry and emission tags. Go ahead.
Good morning, everyone. Sorry. My name is Chuan Feng. I'm currently a postdoc at Texas A&M University. It's a great honor for me to present our recent work titled Distinct Efficacy of Regional Emissions in Affecting Global Methane Concentrations, a modeling study with interactive methane chemistry and emission tags. This is a collaborative work with Dr. Yang Xu from Texas A&M University, Dr. Benjamin Gaubert from NSF NCAR, and a PhD student, Mohammed Amin Marizai from University of Arizona. So methane is the second greatest anthropogenic greenhouse gas. So understanding the impacts of its regional emissions are crucial for effective methane mitigation strategies. So in our study, we run two sets of simulations, the baseline and the no emission simulation. They all cover the years from 2014 to 2019, and they use the improved short-lived halogen chemistry, and the methane emission data we use is the GCP 2020 posterior data. And for the baseline simulation, we include tags of the total emission, Asian emission, Europe emission, and the North American emissions. We'll talk about this later. And all those simulations are using setup by Marizai et al. And this study is following previous presentation by Dr. Gaubert. And the LCLH chemistry is based on the work of Dr. Fernandez, and the GCP data is the work of the team of Dr. Sanos. So this figure shows the difference between the default CESM model and our emission-driven model. This shows the surface concentration of methane, and it's obvious that the default model, there is no longitudinal variations, and our emission-driven model shows clear spatial patterns. And we compare our model simulations to the observations in these figures. Panel A is showing the global map of the correlation between our simulation and the ground observations. And the panel C and D are zoom-in maps. And the statistics in panel B shows that most of the correlation are greater than 0.7. And the bottom panels here, we show our simulation in orange color, and the default CAM-CAM simulation in blue, and the observation data are in black. So this result shows that we have good agreement with Global In-Situ Observation Network. And the observation data we use is the NOAA Methane Global View Plus, the OBSPAC data. And the key innovation in our research is the tagging technique. So this technique draws inspiration from studies on aerosol and CO transport and chemistry, and enables attributing methane to different emission sectors and regions. By tracking each methane tag, our approach provides insights to the contribution to the atmospheric burden at specific locations and times for each tag, accounting for spatial and temporal characteristics of related chemical processes. And specifically, in addition to the baseline simulation with total methane emissions from all regions, we implement regional emission tags for Asia, Europe, and North America to quantify methane concentrations attributed to each source region. So this figure shows how the model works, how the emission-driven feature works. Firstly, we got the total emission data. Then based on that, we create the emission data for each tag. For example, in the middle column, this one is the emission data for Asia, emission data for Europe and North America and other regions if needed. Then the model reads in this emission data, and after transport and reactions, the model outputs the concentration of the tags on the right. So the first panel shows the concentration of methane from Asia, and the second one shows the concentration of methane because of the emission of Europe, and the third one shows North America. So we got the time series of the methane tags, and in this figure, the simulation from the no emission run is plotted in black dots. And the relative growth of global mean methane concentration compared to this no emission run is plotted in color. The green is the European tag, the red is the North American tag, orange is the Asian tag, and blue is the global total concentration. And we noticed that Asian has the greatest increase in global mean methane concentration because Asia has the strongest emission. But our question is, do they have the same efficacy in increasing the global mean methane concentration? Or in other words, if we have a megaton of methane, is there any differences if they are released in different regions? So here we define the term efficacy of methane emission. It is the increase in atmospheric methane concentration per unit cumulative methane emissions since January 2014. And the equation is shown here. This is the efficacy, and the C tag is the concentration of the tags here, and the C0 is the concentration from the no emission run. And here it is the cumulative methane emission since January 2014. And the unit for this variable, and the unit for this variable is ppb per megaton of methane emission. Here is this equation again. and we plot each term in different panels. This is the relative growth or the numerative, or this one is the denominator of in this equation. Sorry. And the third panel is the efficacy. Because of the definition of the efficacy, there is a accumulation term here, so they are descending as time goes on. But we noticed that the efficacy from Europe is the highest of it among all of them, and which means the methane emission from Europe has greatest efficacy. And in panel D, we plot the ratio between the regional efficacy and the global efficacy. So the global efficacy here is 1, and we noticed that the efficacy from European emission is around 20% stronger, higher than the global. On the right, we plotted the map of the efficacy. The first column is showing the result using data from 2014 to 2016, which is the first 3 years, and they have higher values of efficacy. And on the right, it shows the result using 6 years 6 years data. The first row shows the global efficacy, total efficacy, and the second row shows the efficacy from of Asia emission. The third one is the European emission, and the last one is the efficacy of the North American methane. We noticed that the European emission have the highest efficacy, and also the regions nearby the sources are under the greatest impact. Also, we noticed that the European emission have a greater impact over the North Pole regions. So why is European showing greater efficacy? We suggest it is probably because of the methane lifetime are different among different regions. So in this equation, it shows the methane concentration following exponential decay, and the lifetime is here in orange. And with our simulation data, we can estimate those lifetime, and the result is shown below in orange. And we notice that the European is showing a much longer lifetime than the other regions. So that makes us think what causes the longer lifetime of methane from Europe. We know that the methane concentration is the highest near the source regions, and then after emission, it will decrease due to transport or dilution or reactions. Therefore, the grids of the values where the values are higher than the 90th percentile, it's giving us information where the most methane molecules are located at. So first, in this figure, we plotted the distribution of all the tags, and we marked the 90th percentile for each tag. And in the panels down here, we plot with the white line, we plot the 90th percentile value. For example, in panel C, this is the 90th percentile value in this white line, and the values higher than that is within this region. We noticed that after emission, a large amount of methane from Europe are transported to the North Pole region, where the concentration of OH radicals are very low, and this results in a longer lifetime of methane emission from Europe. So in summary, we utilized the CESM2 with emission-driven methane feature, short-lived halogen chemistry, and tagging technique, tracking 3 representative regions. We conducted the 6-year simulation, and the simulation's simulated concentration shows reasonable agreement with observations. We estimated the methane lifetime and found that the lifetime closely reflects the OH concentration along the transport pathway after emission. And European emissions have the greatest efficacy in increasing the global methane level, mainly due to their prolonged lifetime over the polar region. However, the radiative forcing from Europe is not necessarily higher due to the weaker solar radiation over the high latitudes. In the future, we plan to work on the diagnostics of radiative forcing for the tags, and we plan to run longer simulations. And in the end, we acknowledge the funding from Spark Climate Solutions and also the computing allocation from CISL NCAR, and also thank NCAR for the traveling support. With that, I'd like to answer questions. Thank you.
Thank you very much. Are there questions? Yes, Aline.
For the really interesting talk. I'm wondering if I understood correctly from your slide, you're actually seeing a shorter lifetime from North America than from Asia. Did I catch that right? I thought I saw 12 years and 10 years, but maybe I mixed them up. But I'm curious if you have thoughts on why the lifetime would be shorter from North America in contrast to Asia.
I think this is just an estimation of the fitting, and the fitting is very sensitive to the parameters. So maybe the length of the simulation and the emission and even the F term here may have an impact. So these two numbers are very close to each other. So we are not 100% sure that they are accurate enough to compare between these very close numbers. But I think we are more confident when comparing a longer lifetime, such bigger difference like this. So thank you for the question.
Hey, our next speaker is Hyun-Dan, is that right? You? Diagnosing the UH response to ENSO and its underlying drivers. So, go forward to it.
Okay, thank you for the introduction. I'm Hyun-Dan Zhu. I'm right now an MIT postdoc, Houghton postdoc fellow working with Arlene. And today I would like to present our work on the chemistry-climate interaction that focuses on the OH chemistry. And we really want to diagnose further into the underlying drivers of how OH respond to ENSO. So I think the two talks before me have already said a good introduction to my works. So we'll also focus on this mystery on interpreting these historical methane trends, given that the methane is a potent greenhouse gas that's second only to carbon dioxide. However, compared to the methane sources, the methane sinks is pretty much dominated by the reaction with hydroxyl radical or OH. So the reaction with OH alone will attribute to approximately 90% of the total methane loss. Therefore, interpreting this historical methane trend is not possible with a constraint on the OH itself. Lacking direct OH observations, the OH is normally indirectly estimated using the inverse modeling that constrained by the long-lived species such as methylchloroform. So right now in the current studies, some studies suggest that this interannual variation in the OH anomaly are in part related to the ENSO variability. So here I show one study while the line represents the methane chemical loss, so you can view it as the inferred the parameter proportional to the inferred OH. And the different lines represent the two different inferred OH constrained by two different methylchloroform observations, and the shaded color represents the ENSO index. So from this figure, you can tell that this inferred OH itself embeds a very large uncertainty, and the signal with ENSO is quite noisy. And the investigation between OH and ENSO is also studied in a cleaner manner using the model simulation in absence of the external forcing. For instance, in Turner et al. 2018's paper, they present these thousands of the OH measurements without any external forcing. And what they find is the simulated OH is not just the white noise process, instead ENSO is the dominant mode of the OH variability. However, there remains a lag in the mechanic understanding of why OH is changing along with different ENSO phases. So if we look back to these OH chemistry diagrams, we can have multiple hypotheses that lead to the OH response to the ENSO from both the OH production side as well as the OH loss side. For instance, under the different ENSO phases, we will envision some changes in the meteorological factors such as cloud cover, moistening, as well as atmospheric circulation. All of these factors will affecting these different parameters that involved in one of the OH production pathways that I denoted here. And also, there are studies suggesting that the lighting NOx emission will also be changing under different ENSO phases, which will contribute to altering these another OH production pathways through the reaction between HO2 and NO. But also on top of that, from the OH loss pathway side, we will also envision the changes in the BVUC emission as well as biomass burning emissions during the ENSO phases that will contribute to altering the OH loss pathways by reacting with the non-methane VOCs as well as COs. But on top of that, among all of these different drivers, what we still don't know yet is how these different processes are interacting with each other. Are they offsetting or are they amplifying this OH response to the ENSO? Therefore, in my project, we really want to address two major questions. First of all, can we detect these robust changes in the OH during El Nino and La Nina compared to the neutral conditions? And also, what are the roles of these different driving mechanisms? To answer this question, first of all, we compose the SST patterns under the different ENSO phases using these 13-member initial condition CESM 2 Wakan 6 model ensembles. For each ensemble member, I calculate the SST anomaly by subtracting out the ensemble average of SSTs, and I also calculate the corresponding Nino 3.4 index. And using this Nino 3.4 index, I can set out the boundary and the threshold that can categorize the SST patterns into the different three ENSO phases, including El Nino, neutral, and La Nina conditions. I can further step up the categorize the SST pattern together, average them over, and get these climatological SST patterns during both El Nino, neutral, and La Nina conditions, shown as a map in the at the bottom. With these prescribed calculated SST patterns, I can attach them to the climate SST pattern climatology for year 2000, and I run 3 different CAM model simulations that are prescribed by these 3 representative SST patterns. And for each simulation, I run the model for at least 7 years to assess the impact of the atmospheric variability. And in CAM, the model itself is by default configured with the interactive lighting NOx parameterization that are based on the cloud top height, as well as the interactive BVUC emission scheme that we normally use the Megan schemes. Therefore, I further conduct this mechanism denial experiment by turning off the interactive BVUC schemes, as well as the these lighting NOx emission schemes. And using these MET-only scenarios, I can further diagnose the drivers of the OH chemistry to respond to ENSO only from these meteorological factors. And by contrasting the first two scenarios, as well as the last 2 scenarios, I can further diagnose the impacts solely from the lighting NOx emission and the BVUC emissions. And also for all our model simulations, the biomass burning are prescribed using the SAS emission inventory, so the biomass burning impact is not yet discussed in this talk today. Okay, so now I will show you some results. First of all is this MET-only scenario analysis. What I'm showing first is these changes in the water vapor during El Nino and La Nina compared to the neutral conditions, and I narrow it down to -30 to 30 latitude beams. That's where the most changes occurred, and the changes elsewhere are relatively small. And I also further dotted the regions with the significant changes at the 90th confidence level. So as you can tell from this map, we do observe these changes in the OH water vapor along with the changes in the SST anomalies following the Clapeyron-Clausius equations, whereas the water vapor tend to increase over the tropical Pacific and decrease during El Nino and decrease over the same region during La Nina. And in addition to that, I'm also showing these changes in the cloud cover, both during El Nino and La Nina compared to the neutral conditions. And these changes are primarily driven by the shapes of the convections. For instance, during El Nino, the convections have been shifting towards the central and the eastern Pacific. That's where you see the enhancement of the cloud cover over the same region. And the convection tend to compress over the tropical Pacific during the La Nina event. So these were showing the changes in the meteorological factors, and next I'm showing you the changes in the water vapor. So in this map, I'm showing the changes in the OH also during El Nino at the top and during La Nina at the bottom compared to the neutral conditions, and the dotted region were showing where the changes are significant. First of all, at the global scale, actually we don't see the significant changes of the global air mass weighted tropospheric OH columns. However, at the different regions, we do find some significant robust signals. Especially over the Indonesia, during El Nino, we find that the OH will increase by up to 7% over this region. And comparing between El Nino and La Nina events, we find these robust opposite changes in the OH over Indonesia region as well as over tropical Pacific. So these were the changes in the OH, and in the next slides, I will dive into the OH budget and try to diagnose why the OH is changing, shown in the previous slides. So what I'm showing first is during El Nino, the changes in the OH production rate at the top and the changes in the OH loss frequency at the bottom. From this map, you can easily tell that the changes in the OH is pretty much dominated by the changes in the OH production rate, while the OH loss frequency stay relatively constant. If we zoom into this Indonesia region and then further calculate the contributions of the individual OH production pathways and the OH loss pathways, we find that during El Nino, the total OH production rate will increase by up to 11% over the Indonesia region, and over half of them were actually attributed to these primary OH production pathways that consist of the photolysis of ozone followed by the reaction with water vapor. And if we further dig into what the individual parameters are driving this increase in the OH primary production rates, we find this competing offsetting process, and it's actually the result of about 16% increase in the ozone, along with about 4.3% reduction in water vapor. Even though we observe the significant changes in the cloud cover, we don't find the corresponding significant changes in the geosingle D, so the ozone photolysis frequency. So next, I'm moving to the lighting NOx emissions. What I'm showing first is the changes in the lighting NOx emissions also during El Nino and La Nina, and then mask out all the regions where the changes are not significant. And as you can tell from this map, only this tropical Pacific, over the tropical Pacific, you can see these robust changes in the lighting NOx emissions under different ENSO phases. However, if you look at the global scales and also include the changes of the lighting NOx emission elsewhere, you will find that this large variation in the lighting NOx emission that are primarily driven by the atmospheric variability over the land. And this is because the lighting NOx emission production over the land is over 1 order of magnitude higher than it is over the ocean. So even though we see these robust signals of the lighting NOx emission changes over the tropical Pacific, it's overshadowed by the large variation led by the atmospheric variability from the land. That's why if we further look at the changes in the OH, these changes in the lighting NOx emission during the ENSO actually leads to insignificant impact on the OH both globally and locally. And last, I'm looking into the BVUC emissions. Unlike the lighting NOx emission, BVUC emission, we do see some of the robust significant changes under the different ENSO phases, especially over this tropical South America. So during El Nino, we find that the isoprene emission will increase by up to 8% during El Nino and decrease by about 2% during La Nina. And looking into how it's affecting the OH concentrations, what we find here is over the tropical Pacific, during El Nino, the OH would decrease by about 3%. However, during La Nina, we don't see these significant changes in the OH, along with the changes in the BVUC emissions. Looking into the OH budget analysis, these are what we were showing the changes in the OH production and the OH loss frequency during the El Nino, and we find that the changes are pretty much dominated by the OH loss frequencies. And zooming into this tropical South America, we find that the OH loss frequency will increase by up to 8.4% over this region, and is primarily dominated by these OH reactions with isoprene, along with about 17.5% increase of the isoprene concentrations. So to wrap up, in these studies, we want to focus on the interconnection of the interannual variability of the OH and the ENSO, and we want to diagnose the drivers of these OH changes under different ENSO phases, including the meteorological factors, lighting NOx emission, and BVUC emissions. Even though at the global scale we don't see the significant changes, we find that these different drivers does lead to pronounced OH changes at different regions. And also, as I mentioned in the introduction, the different ENSO phases will also lead to the changes in the biomass burning. That's why in the future work, we want to further look into how these changes in the biomass burning will also affect the OH budget. I will end here and happy to take questions.
Hi, nice talk. So I guess you were showing the annual average maps, and all the analysis are based on the annual data. I was wondering if you have also looked at the seasonal, like summertime, and if it matter at all.
Even though I'm only showing the annual changes here, we've been looking at like the monthly variations of the OH, and we even look at how the OH is responding to ENSO at like near the surface or in the upper troposphere. So both seasonally and vertically, we find pretty much similar results as the annual OH response.
I guess I'm curious, like for the isoprene response, then does it also leave then a fingerprint in the ozone and the carbon monoxide that's being generated from the isoprene increases? Like that, and are those realistic, I guess? I'm curious.
Yeah, that's a good question. So if you look at this OH budget analysis here, but it's only focused on the tropical South Pacific America, you find the most changes are these like instantaneous increase in the BVUC concentrations. But yes, if you look at the larger domain, I would expect also some of the changes in the CO that along with the increase in the isoprene emissions. But the changes is not like very robust, very significant in terms of the OH budget. But we were looking to the CO budget as well as the ozone budget, given all the model simulations are saved out there.
Any other questions? Is there anything online?
Thank you.
Okay. Later. Thank you very much, and we'll talk more about this OH and methane lifetime, everything in our discussion. But before that, we have our last speaker, which is Sean Honemekel online. And he is talking about the CSM chemical forecast, the summary of capabilities, and what's next. Okay, thanks, Sean, for joining us online, and please go ahead. We don't hear you yet. Maybe, I don't know. Have to unmute?
Let me try here again.
Now we hear you. We hear you now.
Okay.
Great.
My video looks, or slide is up there. I'm gonna just talk about the CESM chemical forecast system that we do in ACOM. And I'm just gonna overview a summary and some of the coming changes to our forecast. And also just wanna highlight the team that also that contributes to our forecast, and Simone and Rebecca and Louisa, who are all there, and then also our IT pros, Garth and Carl. And this is just a quick little demo of what our forecast can do. This is just a loop of CO fires from the beginning of the month, kind of highlighting the Canadian fires that have been going on. And so this is just one of our pre-visualized forecast products. And another example, this is another version of our Wacom CO fire product, just overlaid on our ACOM Worldview product, which is kind of an offshoot of the NASA Worldview viewer. Similar depiction of the Canadian wildfires. This one's from specifically June 1st, and it shows the Wacom CO fire forecast product in the white box, and it's overlaid with the errors, aqua errors, CO up in the middle, troposphere. And it's just kind of a nice example of how you can sort of merge these two products together in the world viewer and sort of visualize what's going on. And so just to overview what our forecast system is under the hood, we utilize CSM 2.2.2, and our comp set is the Wacom Specified Dynamics FWSD comp set, and we do 10-day 0Z forecasts every day. And we've been doing these every day since 2019. And there's actually 2 parallel runs that we do. And the only difference between these runs is the biomass burning emissions product that's fed into it, one being FIN and the other QFED. And these both run on a 1 degree horizontal grid, the Epson finite volume grid, at 88 vertical levels, and there's just a little depiction there of the vertical resolution that hopefully you can see. And our levels cover the surface to the thermosphere, and we get about 1.2 kilometers resolution in the UTLS region, 1.2 to 1.5 in the middle atmosphere, and below that I think it averages out to right around half a kilometer or so. And this is driven with the NASA GEOS-FP product, and we are nudging it with TU and UV winds, and the current anthropogenic emissions package that we use is CAMS version 5.1. And this is just a breakdown of the system and how it runs. And so the way we have this set up to run is it's a bunch of different tasks chained together using PBS Pro. This way we can predetermine the resources that are utilized for each task, and we get the added benefit of efficiency with being able to chain the job so that as soon as one task is done, it automatically starts the next task or tasks. And the model, of course, is run on Derecho, and then everything else is run on Casper. And the system can be called via the terminal if we need to run a specific day or run a specific task, or just set it on a cron to let it run automatically on its own, which is what we normally would do every day. And so just some of the individual tasks here, we download and regrid our meteorology. We do our biomass burning emissions with QFED or FIN and update those emissions. We set up the XML files automatically in the software to run the model and then run it. And then all the post-processing is done after that, where we convert to pressure, calculate any additional quantities that we need for our forecast, and do all of the plotting. And then all that information is archived and distributed as needed. We distribute to several different locations and plot a few different things, which I'll show here soon. And then there's a cleanup process that keeps everything nice and clean, since we run this on a scratch space. There are some challenges that come along with doing this. One of our major bottlenecks are the meteorology downloads. These are 10-day forecasts, and this equates to 818 files that we have to download every day. And in total, that comes out to about 243 gigabytes worth of information. And server slowdowns are not uncommon, so we have to deal with that quite a bit. There's also the usage of computer resources. We use about 20,000 core hours a week, which by itself isn't a significant amount, but that does add up over time. And we do share those resources on the account that we use, and so that can be a challenge from time to time. And then, of course, when we get to the end of the fiscal year, people competing for resources, that can also pose a challenge. And that ties into our time constraints, because we do need to finish our forecasts in a timely manner. Since it's cumulative, today's forecast always relies on yesterday's forecast to use as an initial condition. And there's the added complexity with larger runs such as Musica, which can take much longer to run. So we aren't necessarily able to do a 10-day forecast if we're using Musica. And then there's some other things like keeping up with the emissions inventories. They're always updating them, and we only keep we have to run them out ahead of time to keep them in the future. And we only do so much of that at once to keep the file sizes from getting too large. And then there's hardware and software changes and downtime, which I'm dealing with currently. And so how these are getting used, one of our primary use cases right now is it gets used pretty heavily as a boundary condition for regional runs. We do this with our own ACOM WRF-Chem forecast that I also run. And there's other people that do this as well with their own WRF-Chem runs. We've used this forecast for field campaign flight planning. We have our own other software suite that we can actually feed our forecast into that allows us to flight plan. And we've used this as far back as in some various forums, as far back as Contrast in 2014, which I think is maybe kind of where the whole forecast system originally, I think, might have actually gotten its start, and then used it very heavily during ACLIP, and it's been used for occasionally with a couple of other ones. There's some external sources that use our forecast. This is an example is Resource Watch. They ingest our forecasts every day, and then there's all the other individual users that use it for various things to do comparisons, model studies, and do, et cetera. And all this information is available in a couple of different locations. One is the Research Data Archive. In their search bar, you can just search for WACM and it'll show up, but otherwise it's dataset 313006. And this is nice because we get a DOI assignment, which allows us to track publications at least to see how much it's getting used. And these are only the analyses, and they're usually a couple of weeks behind real time, just in case I need to do any reruns. And the second locations are our own ACOM forecast page. Also easily can be found with a Google search, ACOM forecasts. and there's a few different products in there to choose from. From a visualization perspective, there's our AECOM Worldview product, which I showed in my third slide. There's pre-plotted forecast maps like the animation I showed in the beginning as well. There's a custom plotting tool where you can go in and pick a date, a variable, a time, a location, and do your own map or vertical cross-section if you want. And then we also store the last year's worth of our analyses and including the latest forecast outputs on our own server. And from there, you can download the full file if you want it, or a subset if you would like as well. And just a few statistics. Since we first implemented it on our server, we've had over 17,000 direct downloads, over 900 unique addresses. And to the right is just the metrics from the Research Data Archive. And one thing to note there is our usage. The usage is almost quadrupled from 2023 to 2024, which is nice to see. And so the stuff is definitely getting used, and our usage seems to be continuing to rise, which is nice to see. And then bottom left is just some of the publications that are on the RDA's metric. And so the changes that are coming and our long-term goals with our forecasts, we're getting ready to make the model version change from CSM2 to CSM3. That'll be accompanied by a COMSET change, switching away from the specified dynamics version and into the newer nudged version. There will be a vertical level change that comes with that, and we'll get the latest and greatest emissions, and we'll probably trim that from one model run instead of two parallel runs to make way for a Musica run. So we'll have a 1 degree at finite volume run, and then eventually a Musica run as well. And then doing some updates to the code base just to improve our downloading and make the code more flexible and get it ready for Musica, and some cleanup. And then once all that's done, hopefully I'll make it available on GitHub for anyone else to use if they want to use it. And long term, as I alluded to, would like to move into the Musica framework and ultimately end up with one unified global and regional forecast system. And these are just a few other finer details from the last slide. Our changeover from CSM2 to 3 nets us quite a few improvements or in bug fixes and code updates. A few are just an improved dust scheme. We get Hemco. As we move into Musica, we switch over from finite volume to spectral element. There's the opportunity to go from CAM6 to 7. We can utilize the moving mountain gravity wave scheme. We go from MAM4 to MAM5, and then a whole host of other things. And then another wish list item will be to add in some diagnostics, evaluation, and some skill. And we have several options for that, such as the Atmospheric Model Working Group, Diagnostics Framework, or the ADF, and then Melody's Monet, which Louisa talked about a little bit ago. And so I think that's most of my time. I think I got about a minute left if there's any questions. Otherwise, thanks for listening.
Thanks, Sean. Are there questions to the chemical forecast? Just maybe to add, if people are interested to look at specific variables when we're updating those forecasts, there are things that may not be necessarily included. I noticed, for example, maybe surface temperature even is also very interesting. There are other climate variables, other things that may be of interest to some people. I think we do want to look into that more, so if people have time to look at it and give input, that would be great. And yeah, So now I think we move forward to some more general discussion again, and maybe we can bring back the first slide set again for that, what we had in the beginning, the morning slide set. So one thing, the theme for this afternoon, and that's great, for the afternoon was the UOH and methane, interactive methane, and very short-lived halogens. And the question came up, can we run this in future development simulations? So just to iterate again from the talk, so the standard version, CSM3, CMIP7, I think at least what we know so far is there was a code freeze, and we're still developing the model. So most likely new developments will not go into those simulations. However, and we come back to the other things. However, our development really, if possible, continues, and we're hoping to put some of the new developments in a new model version. So one thing is definitely the TOVX scheme that is in progress. And then, as we said, the short-lived halogens and the interactive methane. The other thing is also the interactive fires, and I talked to Dave Florian, so maybe that will be some focus we want to look into to really have also, and another thing is the interactive CO2 emissions and fire emissions. There's a lot of more interactivity that we can put in the models and that we can get different answers. I think that will be really interesting and hopefully something we can all work on together as a community to contribute. So thoughts on that? Anybody wants to add anything or ask questions to our plans? And definitely it's good. Yeah, Rafa working on it already to implement new VSL in the development version, and then going over to CMIP7. We are limited so far by the developments of CMIP7. That needs to be finalized so we can get final simulations and experiments to get started. Okay. Yes, question.
Question about the methane emissions and whether interactive wetland is part of that model or what the plans are there.
I don't see, oh, there's Ben. Ben, do you have an answer for that? We don't hear anything, I think. So maybe you have to just go and speak in. There's another mic in the back, Ben. Maybe you can use that one.
Okay. So yeah, it's kind of lagging. There is no funding in CLM group to work on this. I've tried to submit some proposals, but yeah. It's offline mostly. Nobody has worked on doing the interaction with the atmosphere, but yeah, it'd be great to do it.
That want to work on that? That would be great. Or others are interested, and then, yeah. So something we need to put on the list, on our wish list for sure. Okay, then other things are what we had started earlier, or at least the discussion on the intercomparison MIPS. As I have a list here, if people are having any intercomparison projects they want to mention that are coming up, or any thoughts on those, where we are going, that would be great. There will be some discussions on CMIP7 simulations in general and where we are going, which is at the moment not clear, depending on funding and other things happening. But we do, I think a lot of people are very keen on finishing CSM 3 and performing standard simulations, also contributing into these future MIPs, GeoMIP, AirCam MIP, and so on. So one thing, no matter what, that is already ongoing is the HTAP simulations, as I said before, and I went really quickly over it. Luisa and Rebecca are leading those, and if people are in the community interested to help with those, if people are interested to perform simulations and analyze them, that would be really appreciated. Any other thoughts?
Discussed yet, Doug or everyone, but for the BSL's MIP configuration, I mean, we will use CSM2 Wacom 6, but I remember the plan was using CMIP 7 emissions, wasn't it, on boundary conditions? So that will be possible. I mean, despite CMIP 7 projects are not continued using CSM3. So that will be possible. So those are ready? Yeah, okay.
Done, and so we are, I don't know if Doug even started the transient CMIP 7 run or is about to when the computer comes back up. It just came back up.
Ben is going to give me the start it.
Interesting. Other thoughts? We are seemingly maybe being hungry for lunch, and people want to just have more discussions. But if there's anything else, please bring it up now. As we conclude this Chemistry Climate Working Group session for today, and yeah, thanks for coming.